right, we're 2 minutes past the hour here, so we'll go ahead and get started. Good afternoon, everyone. Thank you very, very much for joining us this afternoon. My name is Desmond Banks. I'm a clinical assistant professor here at the Boise State University School of Public and Population Health. I also have the luxury and privilege of being the chair of our continuing education committee. I just want to thank all of my colleagues from the committee today and welcome to our first continuing education session of the 2025 to 2026 school year. We're in for a treat today. Today's session, as you can see from the title screen, is titled Understanding Large Language Models, an Introduction to AI, Artificial Intelligence for Public Health Professionals. We are just delighted and privileged to have Dr. Casey Kennington presenting today. Dr. Kennington is a professor within the computer science department here at Boise State University, and it was just recently, of this past month, named Dr. Kennington was named the Boise State Foundation Board Endowed Professor of Computer Science, marking a milestone here for computer science within the state at Boise State University. So without further ado, I'm gonna go ahead and mute myself and allow Dr. Kennington to present today. Thank you very much. Over to you, Dr. Kennington.
Thank you, Desmond. That was a nice introduction. Hello, everyone. It's nice to be here. I have a talk today for you that I've given a few times and I've fine-tuned, so every time I give it, it gets a little bit better. It's about large language models, and to get us started, I want to give a little bit more bio, just so you know that I'm not a complete fraud in telling you that I know about some of this stuff. So my PhD was actually in linguistics. So language has been something that I've been very interested in for a very long time. And applying that to computation is something that is really what I've explored for the past 2 decades. I teach courses in data science. I teach a natural language processing course. And we've covered language models since 2020. You might mark that that's before ChatGPT came out. And research methods in deep learning and spoken dialogue systems course. Some research, you might find it interesting that my master's thesis was in language modeling back in 2011. Of course, the language models of then were very different from the language models of now. And some other work in enriching large language models with additional information, infrastructure, all kinds of stuff. So this stuff is relevant. It's research that I've been doing for a while. But of course, in the middle of all of that, in November of 2022, something crazy happened, and that's when ChatGPT was released. And you've used a language model before, you've used AI before. Today I'm going to focus on the language side. I know that there are applications such as image or video generation, and those are worth the discussion and worth talking about. But today I'm going to focus on language models because that's my particular area of expertise. So you've used ChatGPT or some like model before. You give it text in the form of a prompt. For example, write an email responding to ... You give it to the language model, and some magic happens, and on the output, it gives you text back. How does that work? Today I want to demystify that a little bit, give you some information about how it works, not the pure math, because that usually gets to a level of granularity that's not very helpful or very interesting. But today I do want to demystify them for you to help you make decisions about when perhaps you should and shouldn't use them, and some good use cases for them. But first, a brief history. A language model is something that captures sequential information, most commonly a sequence of words in a body of text. For example, if I say the words, I would like 2 scoops of what? You have an answer. Most of you would probably say ice cream. Some might say guacamole. I don't know. I hear the word model, but what even is that? A model is a formal or mathematical representation of a phenomenon. In this case, language, ill-defined, but as a sequence. So that's kind of the main idea here. So back when I was doing my master's thesis, we were interested in language being modeled as a probability that a word follows another word. So it's a simple probabilistic function. Don't let this scare you. It's really just the probability of a word that's following words that came before it is the count of the current word divided by the count of the words that came before it. So it's nothing very complicated. For example, if I saw a cat on the mat, I can break that down into the probability of the word I coming in the sentence, the probability that I follows saw follows I, and that A follows I saw, and so on. You can compute this, estimate these probabilities by just counting up words in a data set like Wikipedia, which you could download today for free and process it with some pretty easy to use text processing tools and come up with these probabilities on your own. What they're not good for, though, is long distance dependencies in language. For example, if I have the sentence, I met Biff last week, I have to say, of all the people I have ever met, he, dot, 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 he refers to Biff, and that was like 12 words ago. Language models of 2011 didn't capture that very well. Counting up words in the word sequence doesn't capture meaning very well. And meaning was something that I was very interested in from the beginning. How do we convey linguistic meaning, semantics into computational models? And it doesn't play nicely with general purpose machine learning classifiers. It's just counting stuff. So it's not very generalizable or useful beyond that. To get to where we are today, now we have to talk about something called neural networks. Neural networks are computational models. The latest version of any AI model is using a neural network, whether it's a language model, a diffusion model, something that transcribes speech, whatever it is more than likely using some kind of neural network underneath, also known as deep learning, but I'll explain why it's called deep learning. Neural networks are inspired by brain science, but of course, the neurons and the way they're connected is very, very different. To say they mimic the brain is very disingenuous, but they are inspired by brain anatomy. This is the only math we're going to get into in this presentation, but I think it's helpful to understand how machine learning works. Here's a simple idea. So you have a function that maps input to output, and you've seen this before, right? This is middle school math. This is a linear regression line right here. And what we want to do is, given some data points, let's say I've collected some data, whatever it might be in these little green points here, and what I want to do is predict, given some x, where a y would be. And I can do that fairly well with a straight line because this data looks like it is fairly linear in relationship to each other. So in order to find the line, if you've ever used linear regression before, usually you just plug the data into something in a piece of code or in Microsoft Excel or something like that, and it comes up with the parameters. But today I'm going to show you kind of how those are found. And if you've taken a stats class, you're like, well, I understand how this works. You need a function first, and the function is y equals mx plus b, the function for a straight line. That's this blue line right here. But what we want to do is find the parameters. And what I mean by parameters is we want to find what m and b are, because m expresses the slope and b expresses where it is shifted up and down on the y-axis. And just with those two parameters, we can represent any line we want to. And then we can plug in x, and then that transforms x to b, or sorry, x to y. In order to find m and b, what we have to do is use a different function called the cost function. And in the case of linear regression, it's called the sum of residuals. So what usually happens is we start with a random m and a random b. Let's focus on m right now, just the slope. So let's initialize our m with just this random number. It's some negative m number. And what we then do is we take the data points and we calculate the vertical distance between each point and that m. I didn't represent it here visually, but you get the idea. And you count all those up, you sum all of that and square it to make sure everything, well, you square everything to make sure everything is positive, and then you sum that. And that gives you a number. The number on its own doesn't tell us much. That just tells it's a cost, but what we need to know is it a cost that can go up or down? So what we want to then do is update it. That means we change b. So let's change b a little bit and calculate the vertical distance again. And we sum everything. We square everything and sum everything up again. And then we can compare the two numbers. The first number that we got from this slope, from this m, and the second number we got from this m. if the number's getting smaller, then we're on the right track. We know that the slope is a better fit to this data than the original one was. So if we keep doing that, we change m a little bit every time, and we finally get to a point where m gets low enough to where if we change it anymore, the cost goes up. And if the cost goes up, we're going in the wrong direction. It means it's getting worse. So what we want to do is stop when m gets to its lowest point. And there's some cool ways of finding this. You can just randomly find a bunch of m values, increment over small changes in m, or you can use first order calculus. That's the way they do it in the real world, but we won't get into that. The point is, I need you to understand this idea of I have data. I'm starting with kind of a random starting point, and then I use the data to update my starting point to make m a better fit to the data. This is the essence of machine learning. All machine learning models do something like this. It's just that they use different functions. In fact, let me show you one of them. One is called the sigmoid. And the sigmoid is our first foray or our first start into what might look like what a neuron does, which is a step function of some kind. In this case, it's not a straight line anymore. Now it's this S-shaped line. It also does something very interesting in that it squishes the output, or y, into a fixed range between 0 and 1. So instead of over here where it was any value, negative infinity to positive infinity, now it's between 0 and 1. And that's really nice because if numbers are between 0 and 1, we can use the machinery of probability and information theory to do a lot of really cool stuff. But here's the function. It's L over something, right? It's more complicated than y equals mx plus b. But really, there's still only two parameters. One of the parameters tells us how far the S can stretch or contract, or how steep it should be. And the other one is the shift function, the shift of where the middle point of S is from left or right, which is analogous to what we were looking at here, which is m as the slope and b as the shift. It's just a different shape of a function that's shaped around the data. And what we do instead of putting the data anywhere, we put it on either this axis or this, or either on 0 or 1. And what this then becomes is a classifier that can classify points into one class or another class. For example, I can maybe use something like this to determine if an image has a dog or cats in it, where dog is on the 0 and cats are on the 1, for example. So that's the same idea, but it's the same idea. Whether we're using the straight line or whether we are using the sigmoid function, it's the same idea. We have a cost function, we update, and it shifts the locations and the stretch or the slope until we get to where the fit of the line is the best for the data that we have. Notice that these things are called parameters. So in this case, m and b are parameters. In the linear case and in the sigmoid case, k and l are parameters. You also might hear words like weight or coefficients. Those are all used interchangeably. And this word will be important when we talk about the size of a model like ChatGPT. But the single neuron isn't all we have. We want to stack them together and use them. And this is a simple idea where you can't maybe not be able to see this, but this is the sigmoid function. But instead of using just one of them, let's use more. So let's use 3 and give them all the same inputs. But then let's stack them on top of each other. Let's get 3 more and have the outputs of the first layer of the sigmoid functions be inputs to the next layer. And we can do yet another layer that tells us if it's 0 or 1. And this is really cool because when we stack these together, now all of these individual neurons can do something different. They can kind of have their own division of labor, that when you pass the data through them, they do their job really well. They activate to 1 or they go to 0, something in between as the data is passed through. And then at the very top, that's where we try to classify if something's in category A or category B. So for example, inputs here could be raw pixels from an image, and the output could be, is it a cat or is it a dog? This is called a neural network, where we just hook up a bunch of different neurons together. They're all just these sigmoid functions. They all have parameters. The thing that makes it deep is just that there are more than 2 layers of neurons here. So there's what's called a hidden layer, and there's at least one of those. It's not deep because it's doing deep thinking. It's just deep because it has more depth in the number of layers number of layers of neurons. But it's very easy to set these up with however many neurons you want in each layer, whatever the depth you want. There's different architectures of neural networks that are out there. But what's really important here is that each neuron has, in this case, one, two, three inputs plus the shift. So this has four parameters, this has four parameters, this has four parameters. And if we count those up, we get 28 parameters for this neural network, which is a lot more than the two parameters we had for the single neuron. A parameter is a capacity for the network to learn something. So every shift, every movement, of every stretch or contraction of the S shape for each of these is doing something to help it learn how to do its job. But it's just even these deep neural networks act in the same way as a simple single neuron or a sigmoid function where you pass it data. It has a more complex function than this, but it has a cost function at the top that tells it if it's right or wrong. And if it's wrong, it does this thing called backpropagation, which goes back and changes the parameters in all of the neurons to a certain degree, and then it updates. And you do this, you churn through the data multiple times, and it learns over as it goes through the data. So if we have neural networks, that's nice. But these deep learning architectures are slow to train and run. They're very handy, they're very powerful, but we can't really do much with them out of the box with language. So let's try to fix all of this stuff at once if we can. To get to that point, I want to explain to you something called computational semantics. And this is actually to me, this is like the coolest thing in the world. This is the reason why I kept going to school, kept taking classes, and ended up doing a master's and PhD, because I wanted to learn about this computational semantics. Really, what is semantics? So what is semantics? The meaning of words, phrases, sentences, paragraphs, documents, the meaning of language. And if I ask you something like, how do humans learn the meaning of words? Well, I don't know. You learned them in school, but did you? How did you learn the word red? You probably learned that before your first day of school. Red is a concrete word that refers to things in the world. I mean, if I ask you to give me a definition of red, you might struggle a little bit. You're like, well, I mean, apples are red. It's somewhere on the color spectrum. Yes, yes. But how does a 2-year-old or a 3-year-old learn what red refers to? They see examples of red things and can derive from those examples what the connotation of red is. That's the meaning. Or the word democracy, which is more abstract. This is different. You can learn this by reading off a definition. So this one, the word democracy is learned by other words, but red isn't. Red is learned by visual examples. So I'm very interested in the dynamic between these two things and other areas. Other words, for example, sour isn't something you see; it's something that you taste. So that's gustatory. Or garlic is something that you taste, but it's also something that you smell. That's olfactory. So there's all these different areas of the physical world where the meanings of words kind of reach out and grab the world, and that's part of the semantics of those words. These words are learned in highly interactive co-location with other people. So children don't learn words by watching TV or reading books. Children learn words by interacting with other human beings in a spoken or signed language setting. So how do we convey meaning to machines in that case? Machines, their brains are different. If you want to use the word brains here, they aren't really brains. It's just very fast processing. They ultimately work with ones and zeros. How do we get semantics of human minds, which we don't fully understand, into computational models? That's the challenge here. Here's an idea. There's other ideas, but this is the one that happens to be in the most use right now. And this is the one, the fundamental underlying conceptualization that works for language models like ChatGPT. Let's take Wikipedia, let's download it, let's take all the text, and there's millions and millions and millions of documents in Wikipedia, lots of examples of text. And let's do some statistics and find the top 1,000 words in Wikipedia, the top 1,000 most used words. And let's take those 1,000 words and say, compare those to every other word. And I'll explain here. So let's say that we have these words, and these words are in the top 1,000 words, or at least these words are up here. Arts, boil, data, function, large, sugar, summarized, and water. And what we want to do is come up with a meaning that is represented by numbers, because computers like numbers, um, such that every word's meaning is represented by a list of numbers in comparison to where they show up next to these other words. Okay, lots of words there. So let me explain. Let's take the word apricot. Let's go into Wikipedia and find all of the times apricot shows up. Let's look around the word apricot, like 3 words before it, 3 words after it, and start counting up other words that we see. So around apricot, we see words like boil and large, sugar, water. And words like digital and information, we see words like arts, data, function, summarized. And what you see is this list of numbers. Apricot has ones and zeros in certain areas, and pineapple has ones and zeros in certain areas. And you can see that apricot and pineapple have ones and zeros in the same places. And the words like digital and information have ones and zeros in the same places, but different from the 2 fruit words. We're getting the idea here of that a list of numbers, if 2 words have similar lists, then they must have similar meanings. And if 2 words have different lists, they have different meanings. This is kind of the foundation of what's called vector semantics, also known as embeddings. Embeddings are a little bit different, but it's the same idea. It's a list of numbers that is, in linear algebra world, is a point in n-dimensional space. So if I just take these 3 spots right here, I can say, well, this is somewhere on the x-axis, y-axis, and z-axis, and this is somewhere on the y-axis, x-axis, and z-axis, and they're in different places. But if you expand that out to many, many dimensions, you have points in n-dimensional space. So some smart people came along and said, instead of just counting up words, let's model this directly using a neural network. Let's use deep learning. So you can give a model. This is a deep learner model that has sigmoid functions in it. For example, you can give it a sequence of words. Pineapples are blank and yellow, and you make it guess the blank word, the word in the middle. If it gets it right, good job. If it gets it wrong, go back and fix the parameters. Make the little s functions change left or right or stretch or contract. And you do this billions upon billions of times with huge amounts of data. And what you get is a model that, when you give it the word spiky, can give you a vector, a list of numbers that's really compact, doesn't take a huge amount of information. And you can look at the vectors and compare them to each other. And we find that words that have similar meanings are actually in similar places in n-dimensional space. So if we flatten everything to 2 dimensions, this is what we get. We get green words over here that are health words, brown words over here that are sports words, computer and internet words over here. So here's I mean, we can't see what the actual words are, but there are thousands and thousands of words in the vocabulary here, and we can see that words with similar meanings used in similar contexts, that is, with similar semantics, cluster together. And this is a really powerful idea, because distance between words is something that machine learning classifiers or deep learning classifiers can pick up on very nicely. So this was the beginning. This came out in 2013. These embedding models, this one's called Word2Vec, but it only worked at the word level. So what we want next is a semantics that goes beyond the word level and gives us a meaning of phrases and sentences, discourse and documents, longer sequences. So some smart people came along and said, let's make a neural network that does that really well, that can capture the sequential semantics very well. I promise no more math, but the idea between attention is a way of hooking up the neurons together. Above, we just saw what's called a feed-forward neural network. Inputs go into the next layer, the next layer's outputs go into the next layer, and so on. Those kind of worked for language, but not really. So some smart people came along and said, why don't we hook them up in such a way that makes words attend to each other? So the neurons are learning something that's very specific to language semantics. And what you get is a lot of linear algebra. But what's really cool about the outcome of this architecture is, if I take a sentence like, the animal didn't cross the street because it was too tired, I can see what it refers to. What are the more likely words that the word it refers to? It likely refers to the animal. And it can capture that from within the model itself, which had not been done before. We've tried it before with a bunch of different ways of hooking up neural networks and other machine learning models, but it just didn't work very well until this thing called attention came out. Attention is a certain type of layer in neural networks, and a transformer is a way of connecting all the layers together. So here's a transformer. Transformer takes the individual vectors for a word like thinking in machines, puts it through these layers called self-attention, and then there's these feed-forward neural networks, which look a lot like the ones we saw earlier. And it has several of these. There's multiple versions of these firing at once. This encoder will make the entire sequence represented as a single set of vectors that represents the entire sequence, and then this decodes it, does something with it like translation or like ChatGPT. You input your prompt and it outputs a response. So this is the underlying architecture that all language models use, something similar to this, if not exactly. To train a language model, it's very strange. There's new ways of doing this, but traditionally it's done like this. You take a sequence of words, like how are you doing today, and you cover one up. How are blank doing today? And you ask the language model to recover the lost word, to guess it. And if it guesses it right, good job. If it doesn't guess it right, it goes back and it updates the model. And within this little box right here is millions of neurons and other little things that they hook up to each other to make it work. But lots of these within a deep learning architecture, lots of neurons that are learning something. So it goes back and changes the parameters in individual neurons. And if you pass this billions upon billions, at this point, trillions of tokens of information, a token being a single word, it will learn something about language, something. It's not learning the same way humans learn, but it did learn something. Or you can do this. It's called next token prediction. I saw a cat on a blank and it guesses Matt. Good job. If not, then it goes back and changes the parameters. And you can even scale this up. Instead of just one phrase, you can give it an entire paragraph, cover up multiple words and have it guess what those words are. You can even give it an entire couple of sentences and have it guess the next sentence. And there's ways of having it accumulate reward, positive or negative, if it gets it right or if it gets it wrong. So this is really powerful. This changed the field of natural language processing in 2017 when the paper came out that introduced the transformer architecture. That's how new it is. We pre-train using generic language tasks like guess the word, or called masked language modeling. And then you take the top off the neural network and you put a new top on top of it, and then you can fine tune on anything you want that's language related. You can do sentiment classification, automatic translation, topic modeling, chat, question answering, all the stuff you do with ChatGPT. And you can use a small amount of data to do that. And this is really powerful. This changed this field forever. Before this, someone would come along and say, I'm going to spend my entire career figuring out the best way to automatically model the translation between English and French, and that's their career. But then they wake up one day, sip their coffee, and check LinkedIn, and they're like, "Oh, what's this attention is all you need paper? Let's have a look at that." And they drop their mug because they find that this one model is better at it's better at doing translation than they've ever done before. And it's not just good at it in English and French, it's good at it in lots of languages. And it's good at a lot of other tasks. So language models, we went from coming up with little machine learning models that did little language tasks to one model that can do a lot of them, and that's the transformer architecture. Early on, the first transformer architectures was this sequence. Then we get to BERT. BERT is a bidirectional transformer that was very, very popular, still is, still widely used. I use it a lot in my natural language processing course. The T stands for transformer. And then if you look over here, you see GPT. And GPT you're familiar with, and you now know that T stands for transformer, and the transformer just means that's how the neurons are hooked up to each other. You also have heard the word P, which is pre-trained. That means that they used something like guess the word or masked language modeling to train it on a bunch of data that they combed off the internet. And G just stands for generative. So generative pre-trained transformer. And then they have 2, and then when they got to 3.5, they added some stuff to it that I'll talk about in a minute to make it better. And that's what gave rise to ChatGPT. This was the pedigree chart as of about 2020. Right now, if I can actually show you here. This is the repository. If you can see this website, it's called huggingface.co. This is the repository where language models live, the open ones. So the coin models, the llama models, Alibaba stuff is here. This is where they're all put. And you can see how many that were created just today. So back in 2020, we might have gotten 30 or 40 new models that were fine-tuned on something or in some language. And now we get one every, let's see, every 30 seconds or so are uploaded, which is pretty cool, but also kind of scary. My research group has quite a few models on here as well that we're working on. But it's really easy to use. It's really easy to access the models and use them in your code or with their API. I'm just showing you that because this pedigree chart we thought was really cool. And now we just have hundreds of new ones literally every day. So with transformer architectures, we get a lot of nice things. We get general purpose machine learning. We get better semantics through vectors instead of just counting words and sequences. And with attention and transformers, we get long distance dependencies, and we get it is slow to train and run, but it's much faster and much easier than architectures that we used before, known as recurrent neural networks. So that solves all these problems, which is pretty cool. So let's talk about natural language generation, or NLG, for a few minutes. Machine translation, dialogue systems, chatbots. So anything you're using ChatGPT is considered a generative model. And there's a lot of different things you can do. You can give it data and it will output a kind of a linguistic description. You can give it an image and it will give you a description of the image, for example. These are all generative tasks. I want to explain to you what happens under the hood with generation. You give it your prompt. This is kind of a weird schematic here, but let's say that these Ys are your prompt, like you want it to write an email for you. So you give it your prompt, in this case, 4 words. What it does is it goes through the language model and then outputs a word, a single word, and it's reprompted. It concatenates that word to your prompt and reprompts it. And then it outputs the next word. And then it concatenates that to the growing output and it reprompts it. So the language model doesn't actually maintain an internal state of any kind. It's just the user interface is doing this magic under the hood that you don't see. But it's when you give it a prompt, it will, as it's outputting, it will reprompt itself until it's done, until some sort of a stop character says, I'm done talking. This is called auto regression. Auto meaning self, regress meaning it's kind of predicting the future. But there's a problem with this. Auto regression is predict the next word based on the input plus the model's ongoing output that can steer the model to repeat outputs. For example, if I ask the model, where does Dr. Kennington work? And it responds, he works at Boise State University, then it would start repeating itself. Boise State University, Boise State University. It would just do this quite a few times until it stopped. That was a problem that generative models ran into 5 years ago. So they invented some things to kind of mitigate that. One was called temperature, one's called top K. So instead of just outputting the most probable word, let's output the most probable 6 words and pick one randomly. Another thing so that's top K. Another thing's temperature, which changes the distribution and kind of messes with the rank. So this is really cool, but at the same time, the small amount of randomness that's added to this, you can see where I'm going with this. The autoregressive nature and the small amount of randomness and the temperature is part of why we get hallucinations. So let's talk about ChatGPT and what OpenAI did that made these language models worth something. Because like GPT-2 had been released and everyone was like, this is amazing, but it's also outputting garbage. Like, how can we fix that? OpenAI said, let's take our GPT model, which is a generative pre-trained transformer. And if you have been awake during my talk so far, you know what more kind of at least conceptually what these words mean. That first little deep learning model that we made that had 28 parameters, we were all nodding our heads thinking that's a big model. Well, GPT 3.5, which ChatGPT is based on, had 175 billion parameters. And remember, a single parameter is a capacity for learning. So the bigger these models are, the more capacity they have, but also the more electricity they require, the more compute they require. So OpenAI massively scaled up this process and made the interface useful. So I'm going to show you some visualizations here that I got from this very nice website. So what they did is they said, let's hire 40 contractors. I think they paid them $1 an hour. At least that's what the reports are. They were from Nigeria, I think. And they would give them prompts. They'd say, okay, human, work with ChatGPT, give it this prompt, explain the moon landing to a 6-year-old. So the human would take this prompt, give it to ChatGPT. ChatGPT would output something, and the human would look at it and say, nah, it should have been like this. It should have been this output. Or they'd change the output and say, this is better. Give that to the model and let it learn, just like masked language modeling or next token prediction, same kind of learning regime. They do this for months, right? There's 40 contractors doing this for who knows how many hours a day for many, many months. And after a while, the model gets better and better, but they want to speed the process up and make the model even better. So the next step is you prompt the model again, that same prompt that you had before, explain the moon landing to a 6-year-old, and prompt it 4 times. And each time, because of autoregression and other things, it's going to output 4 different outputs. They're going to be slightly different. The human reads all 4 of them and tells the model which ones it liked best. So it might say, like the 4th one better than the 3rd one, and that one was better than the first one, and the first 2 are about the same. Tell the model that. Let it learn from that. So do this for a few months with 40 contractors, and you can get through a lot of prompts very quickly, and it gets better and better and better at its capabilities of interacting coherently, somewhat coherently. So the last step is what's called reinforcement learning with human feedback. This was a very cool thing that they came up with that became the industry standard for a while. There's some other new ones out now called proximal policy optimization. So let's give it a new prompt that it's never seen before, like write a story about frogs. It outputs the story, and all the human has to do is say, thanks for that story, or can you make the frog maybe this type of frog? It learns from the interaction itself how to improve. And that's really, really cool. That means it is always learning from you as you're interacting with it. It yields knowledge to humans for better or for worse. And people have used that for marketing purposes and nefarious purposes and so on. But let's just recap. Better models using deep learning, using the attention transformers architecture. We have more data, bigger data sets than we had 10 years ago. And improved meaning representations known as embeddings, right? The words represented as lists of numbers or vectors. And improved training regimes, so the masked language modeling. Put all that together, we get language models that are very powerful for any task where language is automatically processed, namely text. More parameters means more capacity for learning. OpenAI took language models, scaled them up, and made them useful. So why should I care? Well, I mean, there's 100 use cases. There's thousands and thousands of use cases for language models like Gemini and ChatGPT, but they're kind of messy, and we've seen some issues that have hit education in negative ways. In some cases, positive. There's been economic effects. Companies with data are the winners. So if you don't have data, you can't really do much. Data collection literacy is not very high among the public. For example, when you use your phone to search for things, it's collecting data about you all the time. And every website you go to, every app you use, data is being collected about you. Basically, if something's free, instead of you paying money, you're paying data. And it got to the point several years ago where companies could predict things about you that you didn't know about yourself. And this was reported that like Target would send ads to women who were expecting, but they didn't know it. They were pregnant, but they didn't know it. But they're getting ads for like baby strollers, and they're like, why am I getting these? And then they find out later that they're pregnant. Somehow Target knew based on certain habits that's what was going on. 70% of companies will adopt one type of AI tech by 2030. Expectations of productivity are going up, impact on automation for manufacturing, marketing, supply chain management, agriculture, healthcare. So there's some good uses for people with disabilities, like transcriptions, translations, things like that. Some industries are further behind than others, and that's because of data. So any industry where it's white collar, where you can collect data from the internet and most of your stuff is online, you have a leg up because that's the type of data that they've used to train these models. But if it's more kind of blue collar worker stuff like carpentry or plumbing, like robots aren't going to do that anytime soon. And it is partly because it's a hard task and the dexterity required for that is higher. But it's mostly because we don't have data sets to train AI models to do those things. So AI in healthcare, there's just direct stuff. I mean, population health is something beyond this even, but they're using AI in electronic medical records for EHRs to do transcriptions. They've been doing that for a long time, but now they're more accurate. EMR field autofilling. So this is kind of cool if like a physician opens up Epic and they have kind of a pre-made template that they need to fill for each patient of a certain type. Like if it's an oncologist of a certain type of cancer screening, then there's like 5 or 10 fields that they have to fill in every visit they have with a patient, and they can just put a microphone in the room when they're having their conversation with the patient, and it automatically fills that stuff in. That stuff's happening right now. Meeting summarization is another thing. That's another thing that physicians have to do. This is nice because physicians hate spending time in front of the computer. It's a real problem for them. Report writing. People in healthcare have to write reports all the time. And if you just have all of the kind of basic information that you need to put into the report, you can put it into AI and it can generate the report in a certain style or a certain format that you want that you need. There are HIPAA issues. There are other issues of security. OpenAI, for example, ChatGPT, they can use them in court cases. So if they're subpoenaed for information, they'll give it on specific users. So there's HIPAA compliance for HIPAA compliance that we have to deal with. That's all I have for today. I didn't talk much about population health, but my hope here is that you understand a little bit more about language models to where you can put two and two together a little bit more and be a little less afraid of them. If you have been afraid of language models and AI, my hope is that I haven't scared you, but that you have a better idea of how they work and how they don't work. What the semantics are, I think, is helpful. Then you know what things they might be good for and things they might not be so good for. I'll go ahead and stop sharing, and I'm happy to answer questions.
All right. Dr. Kennington, thank you. Thank you very much for blessing us with your time, your expertise, and just unparalleled acumen in this area. We're all very, very blessed. And at this time, um, I would like to open up the floor for questions. You can feel free to unmute yourselves, or you can also type it within the chat here, and we'll read those off. So again, thank you, Dr. Kennington. And now we're in Q&A time. Don't be shy. Again, you can unmute yourself, or you can go ahead and put it within the chat. All right. While others collect their thoughts on their questions, Dr. Kennington, I have a question for you. One, if I had you as a tutor or assistant, perhaps I wouldn't have to retake some of my statistics and calculus courses. So where were you, then when I needed you? But no, just being serious here, I've done a little bit of research on this. All right. And so my first thought from viewing your presentation, it's like, wow, we have public health is behind, right? We're kind of behind the curve on this. And I'm just, I'm saying that was just kind of my initial gut reaction about this, back it up here with, just some, qualitative feedback. And I believe in 2018, there was, one university that offered a bachelor's degree in artificial intelligence. I believe Carnegie Mellon was the first based upon these resources. Yep. But as of today, I mean, they're well over 30. And so when I was looking at, I didn't see our program of, within that list of 30. So my guess is that they're, even growing. So for you to try to whittle down, so there's a 4-year degree, so we have universities offering 4-year bachelor's degrees, 4 years of thought into a 1-hour session, or really to 45 minutes, and so tomorrow it's going to be more. We're going to be further behind. We're going to offer more. One, just if you can speak about the 4-year degree that we're now offering at Boise State, but two,
sure.
How do we get better engaged other than offering presentations like this, right? How were your thoughts on public health better engaging with scientists such as yourself to make sure that we're not being further left behind in the
Sure.
artificial intelligence race?
Yeah, a bit about the AI degree. That was about a year and a half in the making. We thought about that was kind of my brainchild. We put it together with a couple people here in computer science and included people from business and ECE and other areas to really design a set of courses that we thought were really helpful, that we thought would really prepare students for not just the theory, but also the practical world of AI that we live in right now. One of the classes, I mean, there's classes in natural language processing, there's deep learning, there's machine learning, there's data science courses, of course. There's reinforcement learning, kind of the standard courses you'd want in an AI degree. But we also have a degree, and when I was looking at other degree programs, they often specialize in something like robotics or health or something like that. We are more geared towards getting students ready for a job in industry. So like we have a class that's called machine learning in production, which is taking AI models, which anyone, can, with a little bit of Python, can grab an AI model and start training it and think, oh, I understand machine learning. This isn't too bad. But scaling that up and making that work for a company, that's a different matter. And when I talk to our industry representatives in Idaho and ask them what's missing, like when students come out and they claim they know about machine learning and they have software development background, what's missing, and they said we want them to be able to productionize this stuff and really scale it up. So that's what that course covers. And I haven't seen that in other AI programs. So we're excited. Our first cohort, it's not a cohort model, but our first group of students joined this fall. It starts right now, or starts this fall. So that's going. And your second question on population health. How can we get caught up? It's a tough one because there are compliance issues. Population or healthcare might be kind of scared to use off-the-shelf models because of things like HIPAA compliance or just security issues, privacy issues. But there are a lot of things that you can use it for to make your own workflow better. But there's some things that people use AI for. I mean, this is pre-language models. I have a colleague here who uses AI models to predict certain, like you can predict an outbreak of a certain sickness in a certain population just by social media posts, by the patterns change a little bit and the things people say. They might actually mention symptoms or that they can't make it to work or something like that, and then you can see that certain areas, kind of like a city, would have a lot of these, and it explodes, and you're like, well, there's something going on there, and you can find evidence for pandemics or certain outbreaks before it even hits hospitals, and that's really cool. The stuff that Moji is doing over in civil engineering, like using like smoke, predicting smoke amounts and what that's going to mean. Like if there's a lot of smoke today, that means a lot more people coming to the ER over the next couple of days, and certain types of smoke, things like that. So there's really cool use cases there. Okay, there's a question in the chat. I agree that public health is a bit behind in this arena, and I think that resources and expertise are part of this. However, privacy, data security, and confidentiality are huge concerns as public health handles incredibly sensitive data. The stakes are high if we get it wrong. Exactly. Yep, well put. So the question is, can you share some tools or strategies to help public health professionals leverage these ML tools? So there's two sides to this. One is you can become more technically oriented by doing something like the data science certificate. Learn Python and learn how to use these ML tools yourself. And you can get it's called the Generative Language AI certificate. What is it? Generative Language AI certificate. And that's where you take some data science classes and you take a natural language processing class and you learn about language models. So you're more on the technical, I can build a model myself expertise. The other end is what most people think of now when they think of AI, and that is, I'm a user of AI. How can I just use existing tools out there and keep them safe? What you have to look for are models that are what are called garden walled. So they're in a space where the data isn't being siphoned off to the company. Like Gemini is supposed to be garden walled for us, but it's hard to say what the fine print is. ChatGPT definitely is not, though there are certain licenses you can get where it promises you that it won't touch your data. Still, is their promise good enough for public health? Maybe not. If you go to, I'll put this in the chat, Boise State.ai. This is a new tool at Boise State, and this is much closer to what you would want to use that has security measures in it. There are several that you can choose from. One right now, all of them are hosted on AWS, but they are garden walled. There's a new one that we're putting up. It's based on Llama 3 that we are hosting ourselves and that we have full control over. Like OpenAI doesn't touch it. It's just ours. It's just ours. So those kinds of models are a good place to start because you know that the data isn't being siphoned off, and there aren't compliance issues. They aren't as powerful often as ChatGPT because they're not as big and they're not hosted on as powerful hardware, but there's also not that many people using them. So the access isn't as locked down. That's still in the works though. That's a project that I've been working on. So I guess educating yourself and deciding, do you want to be on the more technical side? Like if you're not afraid of math and you think programming sounds kind of interesting, there's some options for you. But if it's more on the usage side, then the hard part is finding the language models that are more secure. And at Boise State, we have some maybe that soon, if not now, very, very soon. At least I know that it's working. I can access it. It's just not public on boisestate.ai just yet, but they are working on that. Once that's out, then you know your data is pretty safe. So thank you for that question.
Great question and
Hey,
excellent
Dr.
answer.
Kennington,
Yeah,
one
Matt.
question. One thing we use AI for, or we can use AI for in public health, is helping with some like messaging and content creation. But it's always really essential that we get the facts right.
Yep.
And AI doesn't always get the facts right. There's hallucinations, right? You create a fact that doesn't exist somewhere. What are some ways that we can like minimize the chances of this happening or deal with sort of hallucinations when we need to be factful in our work?
Right. So in earlier in my talk, I mentioned the auto regression and the slight amount so the temperature value. So there's these hyperparameters that you can tune. If you kind of turn all those off and say, just give me the best word, then it's less likely to hallucinate, but it's also not going to give you, it's going to be more deterministic. In other words, if you give it the same prompt, it will give you the same output. And people don't tend to like that. But at least it's going to be what I would call as honest as possible, even though I don't know if we can claim that a model is being honest. It's at least going to give you as the highest probable information based on the data that it's been trained on, less likely to hallucinate. But in order to have that model, you have to have access to the hyperparameters, which we are trying to do in boisestate.ai. Give you the ability to go in and say, I want these settings, so it's not making up as much stuff. That doesn't guarantee that it will output the right thing, that it will give you the right answer, because it has the data that it's been trained on. And if the data that it's been trained on, the way it has synthesized all that information isn't correct, then that humans just have to verify that. That's a big problem with language models right now. And people are working on that. To me, the answer isn't in as much how it's modeled as much as it is in how it's learning and representing the semantics. Because if it doesn't understand the meaning of words, like does it even have a chance to say things that are correct or incorrect? Right now, it's guessing, as it were, with just statistics.
Thank you very much.
I know it doesn't solve your problem of, but that's kind of the way it is right now, as I see it. It's a good question though.
Question. Great answer. Any other questions? Feel free to unmute yourself, or you can go ahead and type them within the chat. All right. Dr. Kinnick, I definitely don't want to monopolize the Q&A part, but just want to, I indicated public health was behind. We're not the only ones, right? I would also say the government. My wife is a federal employee. She works for Department of Health and Human Services. And I just remember several years ago, her boss asked her, hey, find out about this AI and chat GPT stuff and figure out how we can better use it in our work. Right. And, my wife is a Marine. She's, computer scientist. So that was a little scary here today. And just earlier, this week, but she was just one of the younger, individuals within the office. So, hey, just made that assumption. And, earlier this week, she forwarded me an email saying that, hey, now chat HHS employees, you now have access to chat GPT. Right. Just, last week when it's, as you imagine, it's been around for years. So what are your thoughts? How do we better engage, just kind of the language and the training and the history of computer scientists such as yourself? How do we engage with policymakers and with government? And if I can, provide an example, if I was trying to explain AI or the utility of AI to a government official, to a policymaker, and say, hey, if we had this, I'll say it had this, if we employed AI at its full capacity during the COVID-19 pandemic, here is what we have done. I'm sorry to put you on the spot by that. I didn't give you that question beforehand, but I'm just trying to, help you out with the answer, just like, in a way that, a policymaker or a government official may better understand.
Well, I mean, government moves slowly, almost as slowly as academia. So it's like when ChatGPT came out and we're getting emails from the provost saying, watch out for this, for cheating, stuff like that. I wrote them and said, I know about this stuff. How can I help? And like I had ideas for how to help, but they had other priorities. They're like, we don't actually care how it works. We're more, I mean, this is kind of what I'm assuming. And they didn't really ask me to come in and say anything until, 4 or 5 months later. Then there was a panel, and then we started talking, and then things started happening. And that's been the same thing with government. At the state of Idaho, we're finally getting more engagement from state senators and Congress people to talk more about this stuff. I mean, they did just release their Office of Information Technology office at the state of Idaho offers some AI resources. I mean, to me they're a few years behind, but at least they're there. Some areas like education, they had to move very quickly, because within a month of ChatGPT coming out, students were using it to do things they shouldn't, and they had to deal with that. And so education is, I would say, as far afield as most. Though there are some areas like agriculture, which has been in the AI world from early on, from before transformers and language models. So I mean, I've always been willing to talk to people. It's just a matter of, are they ready to have the conversation? But in some cases, it's not a priority until it's a priority. So with population health, that's something that I don't know about as much as everyone else in this room. But that kind of leads to this other question: is there, from Ashley here, is there any collaboration with computer science and public health program within Boise State? Would be great to see opportunities to partner. There are some. So like I go to meetings with other data scientists, and there are some people from population health who go to those meetings, and we talk there. And sometimes there are like senior projects in certain programs where population health people work on projects with computer science students or data science students. So that happens. It's just it's fairly small scale at the moment. But what I see as encouraging is there's I don't remember the name of the program. It's Kirk runs it, but it's a data and healthcare kind of a thing. It's not necessarily population health, but it's moving in the right direction. So there's more of that happening. I agree. It might be a little bit behind, but these new tools can maybe help things catch up a little bit.
Thank you, Dr. Kennington. Based upon the feedback today and our attendance, I imagine that you will be further solicited for engaging those partners and just, discussing and just, engaging where the engagement needs to be made for this fast evolving field. I cannot thank you enough. Thank you to all who presented today, who attended today, I'm sorry. And please keep your eye out for an invitation for next month on our next continuing education session, where we'll explore youth vaping, what parents and public health professionals need to know. Again, everyone, we keep these tight within 1 hour so that you can manage your meeting schedule. So we'll be concluding now. Thank you again to Dr. Kennington, and thank you to all to join today.